Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at a very interesting integral, so stay tuned as we solve the integral together. Okay, so the question is asking us to show that n times I of n is equal to 16 into n minus 1 times I of n minus 2 to the power n times the square root of 3 for all n greater or equal to 2, provided I of n is equal to the integral from 0 to 2 of x to the n divided by the square root of 16 minus x squared dx. Okay, so this is actually a further mathematics question, though in this video I'm actually going to make it look more of mathematics. Okay, so I believe you as a student who offers further maths, when you see questions like this, the first thing that comes to your mind is integration by parts. And basically we know how the integration by parts formula was brought about is basically from the product rule in differentiation. So I'm going to introduce a new function, and in that function, when we differentiate that function using the product rule of differentiation, we are going to see how this integrand will come into play. So we are basically not going to use integration by parts, okay, but we are going to use product rule, and then later we integrate. So follow the solution keenly. All right, so I'm going to pose a function y equal to x to the n times the square root of 16 minus x squared. At the end, I'm going to tell you why I'm using this function. Okay, now I am going to differentiate both sides with respect to x. So when I differentiate the left hand side, I have dy by dx. Now differentiating the right hand side, I'm going to use the product rule, where I'm going to keep one quantity constant, I differentiate the other, and I keep the other constant and I differentiate the other, and I add together. So if I keep the square root of 16 minus x squared constant, I'm going to differentiate x to the n, and I'm going to be left with n times x to the n minus 1. So that gives us the derivative of x to the n. Now I need to add it. So now I am going to keep x to the n constant. I'm going to differentiate the square root of 16 minus x squared. When I do that, how do I differentiate the square root of 16 minus x squared? I need to differentiate the interior, which will give me negative 2x. Then I drop the power, the square root. If I want to write the square root of 16 minus x squared, I can write it as 16 minus x squared to the power half. So I'm dropping the half. So I drop the half, and I differentiate 16 minus x squared with respect to x. Then I multiply it with 16 minus x squared to that power minus 1. So half minus 1 is negative half. So this is basic differentiation by chain rule. All right, so this can be simplified. The first term remains unchanged, and then the second term, we can write 16 minus x squared to the negative half as 1 divided by the square root of 16 minus x squared. So if we further find the LCM, we are going to get this, noting that x to the power n times x is equal to x to the power n plus 1. This negative becomes negative. Positive times negative is negative, and then half times 2 is 1. All right, so the LCM is the square root of 16 minus x squared. When you multiply with this quantity, you just have to square the square root of 16 minus x squared, which will basically give us the 16 minus x squared. Now if we expand, we have nx to the n minus 1 times 16. We have the first term here, nx to the n minus 1 times negative x squared. We have the second term, then minus x to the n plus 1. All right, now from there, this is just the previous information we had. So we try to bring like terms together. X to the n plus 1 is common between the two terms alongside the negative sign. So if we factorize it from the two terms, you are going to be left with n here, and we are going to be left with 1 here, since you are factorizing with the negative sign. Now from here, we clearly see that our dy by dx, we can now separate this ratio, this fraction, into the sum of its partial fractions. So we have nx to the n minus 1 times 16 divided by the common denominator minus x to the n plus 1 times n plus 1 divided by the common denominator. Now these functions are clearly continuous in the interval 0 to 2, okay, and clearly defined. So we can integrate all through. So I'm going to integrate both sides with respect to x and integrate dy by dx with respect to x from 0 to 2. I'm saying it again, I am able to integrate because the functions involved here are clearly continuous and defined on the interval 0 to 2. So when we integrate both sides with respect to x from 0 to 2, now this is what we have. If we integrate the left hand side, the dx cancel and we'll be integrating dy from 0 to 2, which will definitely give us y, and y is x to the n times the square root of 16 minus x squared. Now I am going to separate these two integrals into the integral of the first function with respect to x minus the integral of the second function with respect to x. Now like I said, when we integrate dy we get y, and then from 0 to 2. Now this we can factorize 16n since it does not depend on x, is a constant out of the integral. We are left with the 16n times the integral from 0 to 2 of this quantity. We also factorize n plus 1 out of the integral since it is independent of x. So from here we can replace 2. When we replace 0 as a lower bound, everything becomes 0. If we replace 2, we have 2 to the n, the square root of 16 minus 2 squared, which is the square root of 12. Now if you look clearly, you realize that this integral is I of n minus 1 and this integral is I of n plus 1. Basing ourselves, I of n is equal to the integral from 0 to 2 of x to the n divided by the square root of 16 minus x squared. So you see the subscript is n and the power of x is n. So that's a relationship. So when the power of x is n minus 1, the subscript becomes n minus 1. And when the power of x is n plus 1, the subscript becomes n plus 1. From here, since we need a relationship between I of n and I of n minus 2, I will go ahead and replace n here with n minus 1. Replacing n with n minus 1, on the left hand side I get this quantity. On the right hand side, take note of the terms in red. I'm going to replace the n here with n minus 1. I replace the n in the subscript with n minus 1. Remember, there's still another minus 1 here, okay, so I still allow it there. I replace the n here with n minus 1. You need to add it to 1 here, and you also replace the n here with n minus 1. You also need to add 1 to it. In fact, we are taking one step behind. So doing that, you realize that the square root of 12 is the square root of 4 times the square root of 3, but the square root of 4 is 2. Now this will simplify. This becomes n minus 2, this becomes n, and this becomes n as well. So from there, what can we conclude? We can conclude that 2 to the n minus 1 times 2 is 2 to the n. Then we multiply with the square root of 3, and then we have the right hand side to remain the same. We can now get to the proof by maybe subtracting or maybe taking ni of n to the left hand side and taking 2 to the n times the square root of 3 to the right hand side, and we have the proof. Alright, thank you guys for watching. See you in the next video. Make sure you like the video, share the video, comment on the video, and subscribe to the channel. See you in the next video. Stay tuned and stay blessed.